Hello folks, this video moves right along in chapter 8 with vectors, this time talking about vectors in the third dimension. So the first day we talked about this stuff was all about two-dimensional vectors, which is, just dealing with a flat plane. So basically the first thing we need to understand is the difference between the second and the third dimension in terms of visual aids. In two-dimensional space, we have an xy coordinate plane like this. And if I ask you to graph a point, perhaps the point, 2, 1, you start at the origin, you go to the right 2, you go up 1, you put your point, and you're done. Okay, now if I asked you to graph the vector, let's change the number here, the vector -3, -4, this would be similar, right? So you'd go to the left 3, and you go down 4. So there would be that point. But if I'm asking you for the vector is going to start at the initial point and then end at that terminal point. So in that case, you actually have the vector going from the origin to that point out there. It's not just a point floating in space. Okay, the third dimension includes x and y, but of course we have a third variable called z. So the confusing part is that its coordinate plane is not the same. Like it's not just like x and then y and then we're going to put a z somewhere. They actually, for whatever reason, and I guess I have to do some research on this, change where they are located. Okay, so in the third dimension, the coordinate plane actually looks like this. So you have the flat 2D space and then the axis that I just drew like pops out at you. Or it depends on how your brain is processing that picture. But either way, the vertical, we'll go backwards. The vertical axis is the Z axis. And so this is positive Z and this is negative Z. The horizontal axis is the Y axis. Positive over here to the right, negative over here to the left. And then the axis that's like popping out at you is the x-axis, positive toward you and negative away from you. Okay, so that's the third dimension in terms of graphing. So let's actually graph a couple of points on it before we get to the vectors. Okay, so go ahead and sketch you another 3D plane here. It doesn't have to be perfect. This one has tick marks in every direction. Just remember to label your axes correctly. So again, vertical is Z, horizontal is Y, the one popping out at you is X. Okay, if I ask you to graph the points, let's do -3, 4, and 2. If I ask you to graph that point on the axis, doing two dimensions is easy because you go -3 in one direction, 4 the other direction, ta-da, you're done. In the third dimension, there's kind of a strategy to it. So basically there's this. First of all, remember our triple goes in order, x, y, z. So you still start at the origin, but along the x-axis, it says -3. So if I were just graphing that point, I would go back 3. So I want you to actually put a point there. And then on the y-axis, it's 4. So go back to the origin. Now you can try to go like 4 from here, from that one, but I want you to go back to the origin and graph 4. And then notice what you just did was if we sketch the parallelogram between these 2 points, draw what that would look like. Right, that creates a parallelogram with the x and y axis. And then on z, it's going to be up 2. So then if I go up 2 on z, I want you to make the parallelogram between z and x. So z and x, that would be these 2 parts of the parallelogram are already there. So just to estimate where the other should be. So something like that. So that would be that parallelogram. And then the only other parallelogram, so that would be like, think about we're trying to build a three-dimensional shape here. We're trying to build a three-dimensional prism. So those are two faces of the prism. The third face is going to come, let me change my, well, I don't want to change it and confuse you. Third face is going to come between the Z and Y, which one, this one's just going to be a rectangle here. So those are your three faces, and then if you're going to make a three-dimensional shape, the point is to continue extending in those other directions as well. And then something like this will give you your three-dimensional shape. Now, your actual point, if we were to follow -3, 4, and then 2, would be back 3 to the right 4, and then up 2. So that would be back 3 to the right 4, up 2. So that's why this point here, this red point, would be -3, 4, 2. So there's a little bit of strategy in terms of graphing these points in three-dimensional space because you have to account for that depth factor. Okay, I want to, this time, that was graphing the point, -3, 4, 2. Now I want us to graph the vector. So let's graph the vector 2, 3, and 5. Oops. Remember vector notation? There's a difference because we're going to be using these little arrows here on the sides of our number. So a vector in three-dimensional space is similar to that of 2D space. We're going to graph it almost as if we were graphing the points. So we're going to start at the origin. And remember x, y, z. So in the x-axis, this is positive direction, this is negative. So if it's a +2 on the x-axis, I'm going to come out 2. In the y direction, I'm going to go to the right 3 because this is positive y. So it'll be 1, 2, 3. And then again, before you do z, go ahead and do as much as you can with these two first. So I'd go ahead and make my parallelogram between those two. And then go ahead and do your y of 5. I'm sorry, your z. I wrote y twice. That should be x, y, z. Okay, z of 5. So start back at the origin. Z of 5 will be 1, 2, 3, 4, 5 way up here. So remember that's a positive z value. Down would be negative. Okay, so then go ahead and you have two more faces to draw. And it doesn't really matter which one you draw first. I'm going to draw this one over here to the left first. And then the other face should be pretty easy, the one between the z and the y-axis, because that one's two-dimensional. It's actually just going to be a rectangle. And then go ahead and complete your 3D shape. So something like this. And then let's go ahead and graph the vector. So if I start at the origin and I go 2 on the x-axis, that's going to be starting here. It's going to be 2 out on the x-axis. Then 3 along the y-axis. So from here, you'll move here along the y-axis. And then you go up on the z-axis 5 here. So then you end up at this point. But the difference between the vector and the point is that this ending point is not your answer. I'm asking you for the vector. So the vector is going to start at the origin, and it's going to be an arrow, just as it is in 2D, to that point. So if I erased everything else, I would have that vector in 3D space just kind of floating there. So visually, that is what is occurring in the three-dimensional vectors. Kind of tricky. It depends on how quickly your brain is able to process that third dimension on a two-dimensional paper that you're trying to draw on right now. Okay, so that's visually speaking. Let's talk about algebra. So recap in two-dimensional space. vectors have magnitude and they have direction. And the same is true in 3D space. They have magnitude and they have direction. Now, direction in three-dimensional space is a little bit more complicated because of the third dimension, and that trig is a little bit crazy. So we're going to steer clear of that. We're mainly going to discuss the magnitude. Okay, so first of all, I want to bring some vocabulary to notation that I've already been using. And the first is going to be about ordered triples. So ordered triples is just going to be like ordered pairs, except obviously for that third dimension. So ordered triples, like ordered pairs, can be used to represent vectors in 3D space. And you can shorthand that if you'd like. So basically there are two aspects to this. Remember, vectors exist between 2 points, right? So a point itself is not a vector. Vectors exist between 2 points. So we have two different, I hate to call them formulas, but that's kind of what they are. If I give you 2 points, so let's say to write a vector between 2 points, let's perhaps call those points P1 and P2. So if I give you point 1 would have the coordinates, and remember these are points. So I'm using the coordinate parenthesis notation. So if P1 has the points x1, y1, z1, and a second point, P2, has x2, y2, z2. If I'm going to write the vector between those 2 points, just like we did in two-dimensional space, then our vector would be written in this notation. So P1 to P2 would be this vector here. And then vector notation is the same, like a little arrow with just the top part of it on top. So that vector between P1 and P2 would be vector notation x2 minus x1, comma, y2 minus y1, comma, z1 minus z2. So this is the first important takeaway from today. If I give you 2 points and I want you to write the vector between those 2 points, then you subtract your coordinates from each other. And maybe let me change this vocabulary here. Basically, sometimes you have to remember, not sometimes, all the time, that the vocabulary is important because of the directional aspect of your vectors. So I'm going to put from point P1 to point P2, because that vector will have different numbers than if we went from the other direction. Okay, so that's how to write a vector between 2 points. Let's talk about how we can find magnitude in 3D. Very similar to the way that we found it in two-dimensional space. And in fact, it's kind of a two-step process. Anytime I ask you to find the magnitude, you need to know the vector between 2 points. So if you do that, if you take the vector between your 2 points, then magnitude we notate by using absolute value of the vector is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And what I want you to notice is x2 minus x1 is literally the first number of your vector. y2 minus y1 is the second, z2 minus z1 is the third. And I just realized I messed up these numbers up here. Oh, I bet y'all are throwing a fit. Okay, it should be z2 minus z1. Okay, so this is the second big takeaway from today, is finding the magnitude in three-dimensional space. So let's do a couple of examples for these. Two-part problems. So number 1, part A. I want you, and again, you can simplify this writing if you want, but here's how it's going to be written in your assignments. Write the ordered triple that represents the vector from point A, which is at -4, 5, 6, to point B, which is going to be at -2, 6, 3. Now, when I ask you this, this is also called writing it in component form. So if you see that verbiage anywhere, that's what that is. And basically, what we'll talk about here in a minute is anytime, it's the components between point A and point B. Okay, so if I ask you to write the ordered triple that represents this vector, this is going to be our first, I'm going to call it formula, circled in yellow up there. Essentially, you're going to create your vector AB, and it's going to equal your x2 minus x1, y2 minus y1, yada, yada, yada. So the thing to remember is from A1, or from point A, that's going to be your first point. So that one is called x1, y1, z1, to point B, that one's going to be x2, y2, z2. Okay, so when we subtract, we're going to do x2 minus x1. So it's going to be -2 minus -4 for the x's, 6 minus 5 for the z's, 6 minus 5 for the y's, 3 minus 6 for the z's. And then when we actually simplify, -2 minus -4 is going to be +2. 6 minus 5 is 1. 3 minus 6 is -3. So vector AB is represented by this notation here. So that's part A. Part B is I want you to find the magnitude of that vector that we just found. So once you find the vector, the magnitude part is easy, because then all you're going to do, so magnitude again is denoted by absolute value of your vector. It's going to equal the square root of your x2 minus x1 squared plus y2 minus y1 squared, blah, 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 blah. But what you have to remember is these are the vector numbers themselves. So when I do that, all I'm doing is taking my three vector components and squaring them. So it want to be 2 squared plus 1 squared plus -3 squared. And then we just need to simplify. So this is going to equal the square root of 4 plus 1 plus 9, which will be the square root of 14. Now, again, you always need to make sure that you are in simplest form, that this number cannot be reduced at all, and it cannot. So you can go ahead and leave it like that. But in the future, be careful if there are square numbers that actually simplify. Okay, let's do another example. I want you to find the magnitude of the vector from point C, which is -2, 5, 8, to point D, which is 3, 9, -3. So find the magnitude of this vector. Now, if you wanted, you could find the vector component first, and basically I'm asking you the same question, but all wrapped up in one, but we're going to have to do these same 2 steps. You're going to have to find the x2 minus x2 minus x1, y2 minus y1, z2 minus z1 numbers, and then you plug them into the magnitude formula, or you could do it all in one. Okay, and since I have the numbers, I'm just going to do it all in one. So you can go straight to your magnitude if I'm not asking you for the vector component. So magnitude will be of absolute value vector CD will be the square root of, again, from C means this is your first point, P1, to D means this is your second point, P2. So it's going to be x2, y2, z2. And then when you plug these numbers in, we go from the second coordinate to the first. So this one's going to be 3 minus -2 squared plus 9 minus 5 squared plus -3 minus 8 squared. And then we simplify from the inside out. So 3 minus -2 will be 5 squared plus 4 squared plus -3 minus 8 is -11 in parentheses squared. If you drop those parentheses, you're going to get the wrong answer. And then just keep simplifying. This will be the square root of 5 squared is 25, plus 16, plus 121, which is equal to the square root of 162. And then if you spend some time trying to find square numbers that divide into 162, it might take you a while, but eventually you should find one that goes in twice. So basically 162 could be rewritten as the square root of 81 times the square root of 2, and the square root of 81 is 9. So your final magnitude of vector CD will be 9 square root of 2. So that was an example where you do end up simplifying your magnitude numbers there. Okay, so this is basically how do you find the vector in 3D and its magnitude. And then in two-dimensional space, we also did some algebra with vectors. We were able to add vectors together. So when that happens, as a just as a recap of some vocabulary, when we add and subtract two vectors, each of those vectors are called your components. We can get a new vector, which is called a resultant. And this vocabulary is from the first lesson that we talked about. Well, we could do the same thing in three-dimensional space. So what example am I on? Number 3. So if I say, let's say if vector S, and I'm going to come back and change my notation here, but if vector S is equal to 5, -1, 2, let me make this font a little bit bigger for you. Okay, if vector S is 5, -1, 2, and vector T is 4, 3, -2. I want you to first find 2S plus 3T. And again, these variables should not be floating variables. I don't have a quick way to do vectors typing, so I got to come back and add them. Vector S, vector T, vector S, vector T. Okay, so we could do this math pretty simple. These 2 and these 3 are just scalars, so we're just multiplying every component or every number of your vector by 2, and same thing for vector T. So this would be equal to 2 times vector S is 5, -1, 2, plus 3 times vector T is 4, 3, -2. So these scalars distribute to every number on the inside. So it's going to be 10, -2, 4, plus we're going to distribute this 3. So then it'll be vector 12, 9, -6. And then when we add these two vectors together, you add number for number. So 10 plus 12 will be 22. -2 plus 9 will be 7, and then 4 minus 6 is -2. So this stands for 2 times vector S plus 3 times vector T. And it's pretty simple, but again, I want to discourage you from doing every single step in your head, particularly for partial credit purposes. If you make a mistake, I don't know where you went wrong, that kind of thing. Okay, one more like this. I want you to find vector S minus 6 times vector T. Oh, my font went back to smaller again. So find vector S minus 6 times vector T. Same idea. Take vector S, which is 5, -1, 2. We're going to be subtracting 6 times vector T, 4, 3, -2. So here's where people tend to make mistakes. Your first vector stays the same, 5, -1, 2. They don't know whether they distribute the 6 or the -6. And the answer is it just depends on your preference. if you're going to distribute the -6, then when you do that, and I'm going to do it in two different ways. If you distribute -6 each time, then your vectors are now being added, if that makes sense, because like you distributed that negative, so now it changes to positive. So then your numbers become -24, -18, and +12. So because you distribute the negative, your sign changes to positive. I think that's a little bit more confusing having to deal with the sign change. So I would do the following. I would keep my first vector the same. I would distribute just the 6. That way you keep your negative sign. So if you distribute just the 6, your first vector stays the same, 5, -1, 2, minus, when I distribute that 6, I get 24, 18, -12. And then, again, you just have to make sure that this negative, you're subtracting each of these numbers as you go across. Okay, so then you get 5 minus 24, which is -19. -1 minus 18, which is -19 as well. And then 2 minus -12 changes to plus a positive 14. So again, the arithmetic is easy, but it's just being very careful about those negatives. And do you want to distribute to have negative numbers over here? Or do you want to distribute the number and then just subtract it on the second step? Okay. The last thing we want to talk about is unit vectors. So from two-dimensional space that we talked about last week, I want you to recall that we had unit vectors. So similar mindset to the unit circle is that a unit vector is literally a vector that has a magnitude of 1. Magnitude of 1 in the given direction of the vectors. So in the x-axis direction, that x vector was called vector I. In the y-axis direction, we had vector j of a magnitude of 1. So as I'm sure you might could guess, in the z-axis direction, continue our alphabet here, we're going to have vector k. So example number 5 is what I'm on. These questions are going to sound like this. Write vector PQ as a sum of unit vectors. Unit vectors. If point P is at 5, -2, 3, and point Q is at -4, 2, 1. Write vector PQ, so this should have vector notation, as a sum of unit vectors. So the first thing to know is that I don't have a vector. I have the points that I need, but I don't have a vector. So that's going to be part 1, is figuring out what the vector should be. So vector PQ, we know, we're going to change our notation, is going to be, it's going to start at P and then go to Q. So this one will be our first coordinates. This one will be our second coordinates. So then we're going to subtract our numbers. -4 minus 5, those are the x's. The y's will be 2 minus -2. The z's will be 1 minus 3. So when we simplify, this will be -9. 2 minus -2 will change to a +4. And then 1 minus 3 is -2. So there's vector PQ. Now that doesn't answer the question. The question is, write vector PQ as a sum of unit vectors. So again, if you recall from when we did this in two-dimensional space, we're just taking our unit vectors, which are now I, j, k. So I for x, j for y, k for z, and writing it as those numbers added up all together. So if we were to add those 3 unit vectors, we would end up with multiplying by scalars, we would get vector PQ again. So that'll look like this. -9i plus 4j minus 2k. This is what it looks like as a sum of unit vectors. You simply take the numbers of your vector, put those as leading, or put those as coefficients to your variable unit vectors, I, j, and k.